else jump in. I have not done the opener yet. So Christian and Skylar. And I don't know who else is remote. All right, so for this opener, we have successfully dated the celestial bodies in our solar system, specifically our solar system, to be just a little bit more than this. But the Earth it's really 4.57 billion years old, to give you a better number. That's not exact. I'm sure it's a little bit more exact than that. And that's true, but how do we know? I mean, we know the sun sparked into existence a little bit more than 4.6 billion years ago. How the heck do we know that that's how old the Earth is? What did we measure?
A tree.
No, not a tree.
Rock.
What type of rock?
Volcanic.
No, what does it say over there? Meteorites. He's exactly correct. So, you can't use carbon dating. Somebody brought that up in one of my classes. In order to be able to measure how much carbon-13 is left, the thing had to be alive. Okay, a meteorite wasn't alive. So 4.6, a little more than that, billion years ago, the sun went, aha, and it started main sequence, and it changed from a protostar to a star. It started changing hydrogen into helium from nuclear fusion in its core, and it turned on, it became a star. And then very shortly after that, like about 100 million years, I would say, and that's a very rough number, but about 100 million years after that, we had what was called accretion of the planets. So you had the sun is born, the star is born, and then its gravitational pull sort of makes these rings of dust start to form, almost like rings of Saturn, but where the planets would be in their orbit. And then those clumps of material in the inner planets, iron, nickel, magnesium, aluminum, lots of the heavier stuff, they start clumping together. And as more and more clumps together, there's more and more gravity. It starts pulling in all the extra little bits, and eventually they clear their orbit of debris because they like inhale it. They bring it in. Well, the terrestrials, those are the ones that are closer to the planet, because our planet blasts all the lighter elements out of existence as far as its atmosphere, spreads it way, way, way further out to the gas giants. We have this no man's land, the asteroid belt, where it couldn't quite figure out, am I supposed to be a planet that's terrestrial? Am I supposed to be a planet that's gaseous? Couldn't make up its mind, and so all those extra little leftover bits in that part made the asteroid belt. Those are our meteors, meteorites, but actually really meteoroids. Those are the same age as the Earth. So are the other planets. So are the comets out in the Oort cloud. And the comets that are out in the Kuiper belt, they're all the same age because it was from the birth of our star. Okay, who else is not here? Does anybody still need this? Okay. I have to do a little bit of formation of the Earth. We are going to come back and do this in depth later. We are focusing on the atmosphere and the hydrosphere, what we breathe and what we can swim in. But before that happens, the planet had to go through accretion. It had to aggregate. It had to be born. It had to come from something. So before we had Earth, we had what were called protoplanets. Just like before we had our star, it was a protostar. Proto just means very early, not fully grown yet. And so we had the gravitational pull of the sun, and it made these disks of heavier elements, and they started to clump together. The inner planets are the heavier metals, the heavier elements. The outer planets are the lighter elements, specifically hydrogen and helium. What made the inner planets terrestrial is because they're so close to their star in their early formation, the sun was like a blowtorch, and it blew the very first atmosphere, which was hydrogen and helium. The very first atmosphere, all of the terrestrial planets was hydrogen and helium. The sun blew it out into space. They went out further, far enough away where that solar radiation still occurred, it just wasn't as strong, and those clumped together into gas giants. And yes, the sun was essentially a giant blowtorch, just a plasma version, not a fire version. Now, we do still obviously have hydrogen and helium here. It's just not common in the atmosphere in its gaseous state. It's too light. It escapes the gravitational pull of our planet. I mean, you guys have let go of a helium balloon before, right? What happens to a helium balloon when you let it go? It goes up. Okay, so I've got wrong class. David, Benjamin, Haley's not here. Haley, Devin. And then I gotta be in the right class. So, Kayla, don't eat in here. No. Christian, you're not in the right seat.
Huh?
Garrett's not here.
Yeah, I know.
Billy, Braden, Austin, Brady. I gotta change my thing up. Why do I have Cooper in two different places?
You said that yesterday.
I didn't fix it. Not yesterday, Friday. Okay. I gotta figure out who I left off. Avery. Emil, Ashton. Your brother's not here today, is that what you said?
Is now?
Are we ready? All right. So this is a continuation from the previous slide. So the sun blasted that hydrogen and that helium further out. You needed that last one. I think it's this one. You know what? I should put my glasses on. Finally done. And I might be able to see for a change if they're not.
What do you got, miss?
How much money do I have? Why are you asking?
Amen.
You talking about in my wallet?
Yes.
I don't know. Oh. No, I have 20 to pay the kids that walk the kid home from the bus, so you can't have that. Yeah. You're nice enough to go over. We still have construction work going on in our neighborhood, and I'm afraid that Tim's going to do something bad to us.
I walked 10 miles
You walk 10 miles, it's good for you, it's good exercise.
back in the day.
Uphill both ways with paper shoes and snow. Whoever said go back, you got it? I'm gonna take whatever it is. Got it. All right, so these gases go further out into the atmosphere, and then they collect with the gaseous giants. So Jupiter, and this is fogging up really bad. Jupiter, Saturn, Uranus, and Neptune. Remember, Pluto's different. Further than Neptune, yes.
So Earth is older than that thing?
No, they all formed at the same time. Within reason. Now, I mean, were they exactly the same second? No. But the stuff that we have to be able to measure are going to be the meteorites, and they all formed at the same time. Beyond Neptune are dwarf planets, Pluto. Sedna is the furthest one out that we know of. And then you've also got your Kuiper Belt. Pluto's in the Kuiper Belt. Those are comets. Those are the recurring comets. Those are the water bringers. We're going to talk about them in a minute. But anything that was left over that didn't form a planet, one of its moons, or a dwarf planet, turned into comets and asteroids. So the asteroids primarily are in the asteroid belt. Okay, it's called the asteroid belt. Then the first ring of comets is the Kuiper Belt, really a disk, it's not a ring. But then the bubble, the halo, or the boundaries of our system is the Oort cloud, and they're the really, really far out ones. These are the bits that we radio date using uranium, Uranium, thorium, and polonium, if I'm not mistaken, is the third one that they look at. There is no carbon dating in a meteorite. Even dinosaur bones. It was so long ago, there's no carbon-14 left. Which is not. They have to use uranium dating. The same process that we do with the meteorites. Y'all ready? So how old is the Earth? 4.57 billion years old, give or take a few million. And we do know that because of radio dating meteorites. Now, I don't know which composition or type this is. There are different types of asteroids. Some of them are more iron-based, some of them are more porous, but they're heavy metals. We are taking a look at how much of a radioactive isotope is remaining in the sample. And by knowing the half-life, don't worry, we're not going to do the math on this. It's really not that hard. It's not bad. But knowing the half-life, and then knowing how much is left in that sample, you can calculate how many half-lives have occurred. Then you multiply that by the half-life itself, and that's how old that substance is. The half-life of carbon-14 is like 5,000 something years. But like I said, that only works with things that were once alive, and a meteorite was never alive. And it can't be also like dead for millions of years. You can't date it that far. So carbon-14 lives are really away. Oh, is anybody else's allergies feel crazy? Yes.
Mine was yesterday.
Mine were pretty bad last weekend. I'm itchy right here in my throat. Ugh. My kid got her voice back. Are you all ready? Yep. Okay. You have this in Canvas. I don't know if in your Canvas you can make this bigger or not. I made it this size so that this paper would just be front and back, so I didn't have to staple it. This is geological time from the beginning of the Earth. And I have to read it from here. I can't read it from there. So the Hadean down here, oh, that bar just showed up. Anyways, down here at the bottom, that's 4.55 billion years ago. That's the first epoch. At the end of that is when we had the very first bacterial life. We'll do this later on, and we'll do dinosaurs and everything later on too. And then after that, go away, bar. It's because I'm moving it. The next one, the Archaea, that was the birth of the oldest of bacteria. After that, we had our first cyanobacteria. That was the first things that could do photosynthesis. And so we had our first atmosphere, the sun destroyed. It just said whatever, and it blasted it out of our thin atmosphere. Then we had what was called volcanic outgassing, which is what we're going to end with. And that made our, like, we would die. Carbon dioxide, ammonia, methane. Trying to think what else was in there. Primarily carbon dioxide. We couldn't survive it, but that bacteria could. And eventually it said, hey, I really like this sun thing. And it started producing oxygen. And then that's sort of what was the beginning of what we breathe today. A very, very, very long process. If you see MYA, that means millions of years ago. BYA would be billions of years ago, because I use that in my notes. All right, so how do we get water? Comets. Comets is the short answer. Comets are primarily ice, and it has dust and rock embedded in it. Now we're going way back to when our planet was a giant ball of molten rock. Like very, very, very early stages, no life. And we were just pelted with comets and asteroids. And so that ice, it's not like it melted and then we had an ocean. That didn't happen. But the Earth sort of ingested all of these rocks as they were being slammed into its surface, melted them, and it pulled all these chemicals inside itself. It was this big molten lava pit, essentially, molten iron. This is an impact crater. I don't know where that one was. I took the picture off the internet. But very, very, very early on, there were more planets than there are now. Our moon is a product of one of those hitting our Earth. Okay, so, and I did not have enough time to go back and look up its name. I know the planet that smashed into us had a name, but it was a little bit smaller than Mars. Okay, so here comes, there were no people, there were no dinosaurs, there was no life, there was no mass extinction. This big, massive planet, a little smaller than Mars, slams into the Earth. And you know when you have still water and a drop of water hits it and it like bounces up? The exact same thing happened, but with a planet. So we have a planet came and slammed into us. A lot of it merged with our planet, but a part of it got thrown out. And the moon used to be a whole heck of a lot closer to us than it is now. Eventually, it moved itself away. Somebody asked me in second period, is it still moving away or is it like lost? I'd have to go back and look that up. I think it's actually moving with us as a unit. So it's moving the same speed from us as we are from the sun as it is from the black hole. So everything is in proportion with each other. But that is what brought the water to us. It just wasn't in its liquid state. Our planet ate it. It gobbled it up. Early Earth was lava. It was molten rock. The reason why it was molten rock is, first of all, there was all the collisions. Collisions causes friction. Friction causes heat. You have molten rock, molten iron. So this, obviously, this isn't a real image of the Earth at that time. Nobody was there to take a picture of it. But this is a representation of what early Earth would have looked like. A giant ball of molten rock. No animals, no plants, no nothing, no bacteria. So what caused the heat were the collisions from the asteroids and the comets and the planet-sized thing that formed our moon. Go forward. The actual compression of the planet itself from its own gravitational force. You put more things in a smaller area, they're going to run into each other more. Running into each other more means there's going to be more friction, means there's going to be more heat. And then also the radioactive elements themselves, specifically uranium, thorium, and I did not put polonium on there, but that one too. Radioactive elements, when they break apart, when they go through fission, fissure, crack, they release energy. That energy then creates heat. We do that in nuclear reactors, like the one in Russia that melted down, Chernobyl. And the one that my dad flew over a few days before it almost melted down in Pennsylvania, 3 Mile Island. We actually flew over the cooling stacks with the boat. I think he said it was like a week or two before that thing had its big scare. That happened when I was little. I'm not trying to age myself. I want to say it was the early 80s, maybe in the late 70s. Let's see.
When you were born.
That's not a nice question to ask.
How? I'm calling you that. When you were born.
Yay! I got all that money put in my account. Now I'm so excited. My house finally, the money went through. Woo, 73. I'm not that old. Here, let me look at it.
82.
When,
82.
3,
54, 78.
54. You get a 0. 3 Mile Island. Let's see. It was in 79. I was 1. So I mean, I was like, I don't remember. It was little. All right. So early atmosphere. I already said our Earth has had 3 major atmospheres. The very first one did not last long at all. The sun blew it out into space. That was hydrogen and helium. We're going to talk about the early atmospheres, all 3, including the one that we're in right now, tomorrow. And then we're going to talk about specifically our atmosphere Wednesday. And then how we measure the atmosphere Thursday. I will not be here Friday. I will leave something behind for you to do through Canvas. I have to go to work also. So 100 million years. So we have accretion. Accretion is just what the planets form. It's no longer dust. It's now a molten ball of death. About 100 million years after that original birth, because of all the collisions, it got extremely hot enough to melt iron. So the entire planet was a molten ball. It was not really lava because there was no atmosphere at the time, but a giant ball of magma. And what this allowed to happen was the heavier elements, which are more dense, did what? Do they sink or float? Something's more dense, what does it do? Sinks towards the center, like iron and nickel. And then the less dense elements, like oxygen and silica and aluminum, what did those do? They floated to the surface. This process is what allowed us to start a crust and a core. Not like today's Earth, but I got a red blinking light on my phone. Is what the original crust and core started forming 100 million years after the original accretion of the Earth. One is tall. What am I doing? I don't know how to look at this thing. Figure it out. So this process is called global chemical differential. I did not give you this image. If you want to, you can go pull it off the internet and stick it on the notes. It's like, not quite convection currents like boiling spaghetti, but it allowed the heavier elements to sink to the middle and start forming a core, and then the lighter elements to float up to the surface and start making a crust. And our core is iron. To figure out how to. This is different from what we do at schools. It says no records. September 18th. I think that teacher. And if you ever want to add extra images in with your Canvas notes, man, I can't remember where I stole that one from. But if you type in global chemical differential, it should pop something like this up. It just means the heavier elements will sink to the center, start forming a core of whatever that element is, i.e. iron for us. Lets the lighter elements float up to the surface. Most of the surface of our crust actually has oxygen in it, in some way, shape, or form. It may not be the oxygen that we breathe. It could be locked in like sugar. Sugar's C6H12O6, but it has oxygen in it. Well, that's glucose. Sugar's C12H21O11, I think. It's been a long time since I've done biochem. All right, so this global chemical differentiation, this one just animated weird the way that I put it in. So remember, the Earth snapped into place originally at 4.57 billion years ago. At 4.3 billion years ago, we had a crust, and we had not a core like this side. You guys have this image. This is the current Earth. This is the way it was back at that time. You had a very large core, which was basically the core and the magma together. One big molten center. Because now, when I was your age, I remember learning, okay, we got a crust, part we walk on. We have the mantle, magma, which turns into lava and spews out of almost said tornado, out of a volcano. And then there was the core, but the core actually has two subparts to it. The very center of our Earth is solid iron because it's under so much pressure. That's the inner core. The outer core is molten iron. And as long as we have an outer and an inner core that are both trying to kill each other, our planet will still be alive. Once the inner core wins the battle and it eats, it turns all of that outer core into solid iron, we lose our magnetosphere, we lose our ozone layer, we get pelted with UV radiation, and everything fries on this planet. We turn into Mars. We don't have this nice cushioning atmosphere that we're breathing right now. And we're still not sure exactly what happened to Mars to cause its core to die.
How much?
A lot.
on it now?
No, not that much. How expensive of a house do you think I had?
Maybe serious, so maybe.
Users don't make that, they don't make that much money. It would be nice if we were paid for all the other stuff that we're doing right now, but it didn't happen. Does anybody still need this one? You still copying it? Like I said, our early Earth, maybe I had a crust, but it wasn't like, it didn't have water, didn't have animals, didn't have plants, didn't have bacteria. It was about 3.5 billion years ago that the first bacteria, the archaebacteria, that they started coming into an existence. And then it wasn't for like an extra billion or 100 billion years. No, 1 billion years. 1 billion years. That's I'm saying that correctly. That we had cyanobacteria, the first photosynthetic organisms. And it wasn't until a heck of a lot longer than that we had that big influx of plants, of which fungus was the first. It was fungus, then it was moss. And I can't remember the next one. I think it was the conifers, the pine trees. And then it was flowering plants. We'll go through all of that. I have to go back and brush up on it. It's been a long time since I've looked at the evolution of life on the planet. All right, chemical composition of the earth. You guys have this too. You have this. I don't know how well it is for you to read it. I don't know if you can make it bigger. I know it's impossible to read on the paper version. So, our whole earth, the entire earth, the biggest percentage is iron at 35%. The next is going to be oxygen at 30%. And then when I add the next two chunks of silicon and magnesium, that makes up 93% of the chemical composition of our entire planet. The crust, however, are the lighter elements, and most of it is made of oxygen, which is 46%. Like I said, I don't know how well you can read the numbers on canvas. Silicon's the next at 26. Or is it 28? Is that 26 or 28? 28%. Aluminum. And an iron is only 6%. We still have iron on our surface, so we wouldn't have rust. It's just nowhere near the amount. But the crust, the three major elements, that's 82% of it. So most of the iron is in the core. Like I said, I don't know if you guys can make this image larger in canvas or not. I tried to fit everything on 2 pieces of paper for paper notes. We will come back and talk about the earth in depth really the rest of this year. Things like weathering, erosion, all the different cycles, the water cycle, the nitrogen cycle, which I think you guys learned like in 8th grade, whenever you took earth science. No, I couldn't give it to you even if I did. It's considered drugs. All right, lithosphere. Litho means rock or stone. The lithosphere is the crust that we walk on, and yes, the very upper part of the mantle. It has to include the upper part of the mantle because otherwise we wouldn't have lava coming out through volcanoes. Magma underground, lava out of the volcano. We will eventually get into plate tectonics. We'll talk about earthquakes, the different things about the structure of the surface of our Earth, since that's where we spend our time is on the surface.
Do you hear about the 9-point-something magnitude earthquake?
Where?
In
Recent? No, I did not hear. That's a big one.
Yeah, it changed like the Earth's spinning or whatever. It shortened our days by a second.
I have not. Is that what? Yes. When did that happen?
That's a while ago.
Let me see. Because the internet never lies, right?
No,
So it was Japan.
I believe.
Well, that was the one in 2011, which was a 9.1. That must be the one you're talking about.
Oh, yeah.
That was a while
That
ago.
was, yeah.
Wasn't that the one that happened right before the whole of a giant tsunami or something like that?
Hiroshima?
Yeah, I think, no, not Hiroshima. That was warheads that we dropped. Hiroshima or Hiroshima, I've heard it pronounced both ways, and then Nagasaki. And then the names of the bombs were Fat Man and Little Boy, and the names of the planes were the Enola Gay and Boxcar. And I cannot remember which plane dropped which bomb and which bomb was on which city, but I remember that from history. History was not my thing.
So the ones who dropped the bomb, they got the most, they got the highest body count.
The only country that's ever dropped a nuclear bomb is the United States. And we got both of them on Japan.
But who was it?
You mean, who was it?
Who was the dude that dropped it?
Oh, the name of the pilot? That I would have to look up. That I do not know. I know the name of the plane and the cities and the bombs themselves. But, yes.
Right.
Did you know that we had a before female president in 1930?
No.
Because Woodrow Wilson had a really bad stroke, but he didn't die. He could still communicate. So he had his wife standing as president.
Really? I did not know that. See, like, I'm not history is not it was not my favorite subject at all. I like math and science. All right, so the next one down, so when we walk on, the outer layer is called the lithosphere, that's the crust. There's almost like a conveyor belt underneath the crust, down in the mantle, that allows the plates to move over them. Otherwise, we would not have earthquakes. So your asthenosphere is almost like a fluid level that allows your plates to move past each other. Sometimes they slide past each other. Sometimes they literally split apart and they make a gap or a rift. Sometimes one plate goes over the other plate. We'll talk all about that later when we hit plate tectonics. Ductile means to be able to stretch out thin like a wire. It does not mean that there's wires underneath the crust. It just means that it's fluid. It can move. And the plates sort of ride along the top of this. You done with this one? Yes. Oh, I have been logged. I got the wrong button. Go on to the right button. All right, the deep mantle. Now we're going further down inside the earth. The lithosphere is the top part. We're going down as we get to a new word. The deep mantle, this is where the magma is. The part that actually comes to us is from the previous layer, but it's supplied by the deep mantle. Almost 3,000 kilometers down. I remember when I was like 4, I had a spoon and I was in the backyard and I told my mom I was going to dig with China.
Oh.
I know a lot of kids have done this before. It is physically impossible to dig through the earth. In fact, I don't even think China is like directly on the other side. I'd have to look at a globe. I don't have one in here. But you can't dig from one side of the earth to the other because you would burn up inside the mantle. You would create a vent down, like you create a volcano if you did that. Well, you can't. You cannot travel through the center of the earth. It's not going to happen. The outer core is molten iron, and then the inner core is solid iron. And the reason why it's a solid in the very center is because of the pressure. You increase the pressure, and it keeps it in the solid state. Now, hypothetically, we did like a magic school bus field trip, right? With the magic of the bus. And we teleported ourselves to the very, very, very center of the inner core, and like we hollowed out like a perfect little bubble for us in the very, very center of the core. What would happen to us? I mean, I know we would be crushed and we would die. Let's pretend that we won't. What would we do in the very center of the earth? We would float. No, we would die. You're right. We were said we would die. You're right. We would die. We would incinerate and we would be like compressed, like we'd implode. We'd squish. But hypothetically, because gravity is pulling on every which way towards you, if you're smack dab in the middle, you have nowhere to go and you're stuck. Once again, it's hypothetical. We can't burrow down into the center of the earth. It's not going to happen. All right, last one. We will come back and do continents as we go along. We do plate tectonics and talk about Pangea and Rodinia and all that. There's a snowball Earth and all these different stages that our planet has been through. But continents, you had all that lighter element material that came up to the surface, then it congealed. And then with plate tectonics, that supercontinent Pangea broke apart. South America fits perfectly in Africa because that's where it came from. But we're going to come back to this later. This is the slide that's going to introduce what we're doing the next two sections specifically. This image is called volcanic outgassing. And very early on, even before there was water, after that first atmosphere, we had all these volcanoes and they were spewing all these different gases and creating a new atmosphere, primarily carbon dioxide, methane, and ammonia. Like, we would die if we breathed it. Like, we wouldn't survive. But there were other things that were spat out too. Water was created in this process. Now the hydrogen and the helium went out, it escaped. Nitrogen did not. And the high amounts of nitrogen, bacteria liked that. And like I said, our first explosion of life, I know it doesn't sound like much, but it was bacterial. And eventually, cyanobacteria, which is photosynthetic. And when those released oxygen, mixing with the other chemicals in our atmosphere, it started switching that second atmosphere, the one that was toxic to us, but the bacteria had a party in, to one that had a lot more oxygen in it. Our atmosphere is almost completely made up of nitrogen gas and oxygen gas. There are other elements there too. There's other gases there too, but that makes up like 99% of our atmosphere. Nitrogen doesn't hurt us. Well, unless if you go scuba diving and you see a shark and you freak out and you come up too fast, then the nitrogen bubbles out of your skin and you get something called the bends and then you can't move and you drown. But the process of taking it from down and deep inside the earth up through these vents and spewing things out is volatile transfer, which is volcanic outgassing. The gas comes out of the volcano. They're really literal in the term for this particular process. And we're going to talk more about that tomorrow. Now, I'm going to pause this and double check online. I'm going to stop my recording. Let's see. Looks like I've got more people.